Okay, so let me first make an announcement that assignment 1 solution is posted. I apologize for it taking so long to post online. I do understand it's good to have feedback as soon as you return the assignment. And we'll try to be better at getting all those solutions up. Okay? So let's start with a summary. So as usual, we've found that we can describe a system, and that system can have many particles in it using the Lagrangian. And hopefully by now you know the Lagrangian is T minus V, where T is the kinetic energy and V is the potential energy. The equations of motion are given by, sometimes people call them just the Lagrange equations, if they're referring to classical mechanics, or the Euler-Lagrange equation, if they're referring to the calculus of variation. So I like to call them the Euler-Lagrange equation, and I think I'll have to update the notes to reflect that better. So the equations of motion are given by the Euler-Lagrange equation. That equation is true for each degree of freedom. And by now you also know by heart the Euler-Lagrange equation is d by dt of di L by di qj dot minus di L by di qj equals to 0. So this leads typically it gives a set of ordinary differential equations for the functions qj of t. Remember, qj are the generalized coordinates of the system. So if we can describe how all the qj's vary with time, we can describe how the system evolves. And because these are functions, typically, to know those functions, we need to solve an ordinary differential equation. And the Euler-Lagrange equation gives us that differential equation. So we're physicists here, and we're not so concerned of how you solve the ordinary differential equation. That's a problem for our mathematician friends. Okay? Now, in general, we have assumed that the qj are independent of each other. And it's because the qj's are independent of each other that you ultimately end up with the Euler-Lagrange equation. There's a step in deriving that equation that says that we can vary all the qj's independently of each other, so that term must be true, must be equal to 0 for all qj. Okay, that was the gist of the argument. However, we can accommodate, I never know how to spell accommodate, I think it has double C's and double M's. Accommodate. Sorry about that. However, we can accommodate holonomic constraints between the qj's and effectively keep more qj's than are necessary. So we may have some sort of constraint between the QJs, so an equation that allows you to express one Q in terms of the other ones. But sometimes we might decide that that might be arbitrary, and we don't want to eliminate that particular Q. So then we have too many Qs. We have more Qs than the minimum number of degrees of freedom. So if the equation that allows us to eliminate the Qs are holonomic, that is, they are a constraint equation between the coordinates, then we know we can use this method of Lagrange multipliers to have these extra degrees of freedom. So these holonomic constraints would be something like an equation, so some function fk of all of the q's equals to 0. So that's a constraint equation, right? We call that a constraint equation. So when we have a constraint equation, we can use the method of Lagrange multipliers. Oops, I'm having trouble spelling today. Lagrange multipliers to build, let's call it an effective Lagrangian. L bar, and that's given by the original Lagrangian minus lambda 1 f1 minus lambda k fk, say, if there are k constraint equations. So then the equations of motion are given by the same thing, the Euler-Lagrange equation, but now it's applied to L bar instead of L. So if you remember, L is T minus V. So T minus V minus lambda 1 F1, minus lambda K Fk. These terms, the lambda K Fk terms, are like potentials. Right? The Lagrangian, we have T minus V, and then we've also subtracted minus lambda 1 F1. So I could call the lambda 1 F1, I could call that maybe V1. And then all I've done is really I've added more terms to V. And so we can associate force, and I'll put force in quotation marks because it may be a torque or it might be something that's almost impossible to comprehend in terms of notions of force and torque. But we can associate a force to these, I'm going to call them potentials in quotation marks, because they're not really potentials, but they mathematically they look like potentials. And so you can have a force, a generalized force, which I'll label capital Qij. Let me put that a little bit prettier. And so we could define these forces as lambda I d by dt of di Fi by di Qj dot minus di Fi by di Qj. So the lambdas are constants, right? These are Lagrange multipliers. And then the f's depend on the q's. So generally the f's don't depend on the qj dots, but they could, okay? But if they don't, then the generalized force capital Qij is just lambda I, or minus lambda I di Fi by di Qj. And that's exactly like sort of normal potential energy. This term at the front there with the d by dt, it's mostly just to handle the case of electromagnetism. That's the only time where a potential really depends on velocity. Okay. And here we've come up with a generalized force here, and it's purely mathematical analogy, right? I just recognized that I have kinetic energy minus potential energy, and then minus these other terms, which are the Lagrange multiplier terms. But because mathematically I just subtracted them from the kinetic energy, just like I have the potential, then I can say, well, these things are kind of like potentials. And so if they're kind of like potentials, then when I take the derivative, when I do the di Fi by di Qj, then that's kind of like a force. And so that sort of makes you think about it. And when you think of a constraint is in general associated with a force. So think of a constraint of a hoop rolling down an incline, which is the last example that we did last Tuesday. There's a constraint that the hoop, for example, rolls without slipping. So for a hoop to roll without slipping, there has to be a force that prevents it from slipping and makes it turn, right? If you had a hoop that rolls with slipping, in principle you could imagine just the hoop sliding without even rolling along the surface, right? You could just pull one edge of the loop and it's just going to slide on the surface without turning. But for it to turn, so to roll without slipping, then there has to be some sort of torque that makes the hoop turn. And we saw last time that mathematically that torque comes about when you try to find the generalized force associated with the constraint equation of rolling without slipping. Another example of a constraint, for example, is a normal force, right? You have a mass that's moving around on a table, and it doesn't fall through the table. So you would write a constraint equation that the mass is constrained to the table. And the reason the mass is constrained to the table is because there's a normal force from the table pushing up on the mass. So the constraint equation of, which is between, only has to do with coordinates. So the constraint equation is that the coordinates of the mass must stay on the table. It turns out you can figure out a force that's associated with that constraint, and that force is, of course, the normal force. So it's generally true that these constraint equations are related to some sort of internal force. Okay, that's sort of like quite a deep statement that we can observe just from the mathematics, without even having the concept of a force, right? Okay, so last Tuesday, we did an example of a hoop rolling down an incline, and we purposely did it with more degrees of freedom than we needed, and then we found the force associated with that, the constraint, to be the torque that makes the hoop turn. And today we'll do exactly the same example with yet another additional degree of freedom. So we'll do it with 3 degrees of freedom instead of the only one that's necessary. Any questions about the sort of summary? All right. And then last Thursday, we just did a series of examples, right? I just worked through a bunch of different problems to give you practice and just applying the Lagrangian to get the equations of motion. And we saw that we got the same results that we would have expected from Newton's second law. And hopefully you're starting to be convinced that this is a more convenient way of doing things. Okay, so I want to start with example 4.5 from the notes. So it's the same diagram as example 4.4. So we have a hoop of radius capital R and mass capital R. Sorry. Oh. Wrong with the notes. The hoop has a radius capital R and mass capital M. Sorry. And it rolls down the incline. The incline has an angle theta. And this problem only has 1 degree of freedom, right? You can describe it, since it rolls without slipping, so it's a hoop rolls without slipping. So we only need 1 degree of freedom. So let's talk about degrees of freedom. We should have a coordinate system. So let me have x go to the left. So possible degrees of freedom that we could use simply the x position of the hoop. We could use the y position of the hoop. We could use phi, the angle of rotation of the hoop. We could use little r. Little r would be maybe a vector of the distance of the hoop from the origin. You can use any of those 4 and to describe the system. But what we'll do instead, we'll choose 3 degrees of freedom. Plus constraints. Alright? And so we'll choose, as a degree of freedom, we'll use x, y, and phi. So let's look at how all of these, the 4 possible degrees of freedom, x, y, phi, and lowercase r, how they're related. All right. So we have, for example, r squared is x squared plus y squared. We have y over x is equal to tan theta. We also have x equals lowercase r cos theta. We have y equals lowercase r sine theta. And finally, we also have that lowercase r is equal to capital R phi. And all of these are related to the fact that on the one hand, it's rolling without slipping. That's really the last equation there. And on the other hand, it's rolling without slipping along the plane. Right, so it has to stay along the incline. That's why y over x is tan theta. So I'm going to write all this into two equations. So let me write the first constraint equation. So we're using 3 degrees of freedom instead of 1. Right? So to do that, we need to have two constraint equations. So let me say the first constraint equation, I'm going to use the y over x equals tan theta. So I'm going to say f1. So this function f1 was dependent on our 3 degrees of freedom, x, y, and phi. I'm going to say that that equation, that constraint equation, is the fact that y minus x tan theta equals 0. For the second constraint equation, I am going to use the fact that y minus lowercase r sine theta equals 0. So I divide that through by sine theta, I have y over sine theta minus r equals 0. But I don't want lowercase r's in here. I want capital R's, or phi's. So I'm going to replace the lowercase r here with capital R phi. So f2 of x, y, and phi, I'm going to write as 1 over sine theta y minus capital R phi equals 0. So those are my two constraint equations. I guess maybe I should put a 3 bars on the equal sign where I'm defining the f functions. Right, so now I have two constraints to form f equals 0. And so f2 I could have just as easily written in terms of x instead of y, right? Because I used the fact that y equals r sine theta, I could have used the fact that x equals r cos theta, and then I would have 1 over cos theta x minus r phi equals 0. But I only need one such equation. Any questions about that, these constraint equations? All right. So from now on, we have one last little step of physics, and then it's all math. So the step of physics here is that we need the Lagrangian. And we want that in terms of our degrees of freedom, right? Our degrees of freedom are x, y, and phi. So let's look at the kinetic energy T. T is the rotational plus the translational kinetic energy, right? So I have a half pi phi dot squared. That's the rotational kinetic energy. And then plus a half m VCM squared. That's the translational kinetic energy of the center mass. Okay? There's a hoop. So the moment of inertia of a hoop is a half mr squared. Right? The kinetic energy is going to be a half. Oh, that's wrong in the mix. No, I'm sorry. The moment of inertia of the hoop is mr squared, right? Yeah. Sorry. The moment of inertia of a hoop is mr squared, not a half mr squared. Because it's just a bunch of point masses that are all at the same distance. A half mr squared is for a disk, but a hoop is mr squared. Sorry about that. So the kinetic energy is a half mr squared phi dot squared plus a half m, and I want to write VCM squared in terms of our degrees of freedom. So in terms of our degree of freedom, that's just going to be x dot squared plus y dot squared. Okay? Now, potential energies, we only have gravitational potential energy. So that's going to be m, g, and ycm. Instead of calling it ycm, I'm just going to call it y because that's the name of our degree of freedom. That's technically a little bit wrong, right? Because if the way I've drawn my coordinate system like this, the y refers to the point of contact here, right? That's the y position. But the center of mass is offset by some small height, right? So my potential energy is wrong because if I call it mgy, then it really should be mgy plus d. But what that does is it adds a constant term, mgd, to the potential energy. And so adding a constant term to the potential energy doesn't change the equations of motion. So we made that argument last time. In fact, we saw that it canceled out. And we'll make it again later more formally, but I hope now that you're convinced that adding a constant term to the potential energy doesn't really affect the equations of motion. Because ultimately you take the Euler-Lagrange equation, which means you have to take derivatives of terms, and so terms that are constant, of course, their derivatives are zero, so they don't end up in the final equations of motion. Alright, so that's why I'm happy with writing the potential energy is just mgy. Alright. Where does my thing for changing pages go? Alright. So we can now write our Lagrangian L sorry about that. I'm going to try to comment at the same time on my computer. Alright, so the Lagrangian for the system in terms of our generalized coordinates is kinetic energy, which was a half capital M capital R squared phi dot squared plus a half m x dot squared plus y dot squared for the translational kinetic energy, and then minus mgy. Remember now we're using 2 additional degrees of freedom, so we need to build a modified Lagrangian that includes the terms with the Lagrange multipliers. So we build L bar, which was equal to L minus lambda 1 F1 minus lambda 2 F2. We have those 2 constraint equations that I boxed in blue in the previous page, right? So that gives us a half capital MR squared phi dot squared plus a half capital M x dot squared plus y dot squared minus mgy and minus lambda 1. So the f1 function we had as y minus x tan theta, and then the second function minus lambda 2 we had 1 over sine theta y minus capital R phi. There's no more lowercase r, so I'm just going to call it r. Okay? So that's our modified Lagrangian. So now we apply the Euler-Lagrange equation. Alright, so remember the Euler-Lagrange equation is, well, the first one is going to be for x. We have d by dt of di L by di x dot minus di L by di x equals 0. So if I do that, let's look at the x dots. So there's only one term with x dots, that's the translational kinetic energy. So if I do di L by di x dot, I get a half m x dot, or I get just mx dot, right? The squared cancels the half. And if I do d by dt of that, I get mx double dot. Then it's minus di L by di x. So if I look at our modified Lagrangian, x only appears in the term that has lambda 1 in it. So that term is plus lambda 1 x tan theta. I'm going to have to do di by di x of that. So di by di x of lambda 1 x tan theta is just lambda 1 tan theta. And then it's minus di L by di x. So it's minus lambda 1 tan theta equals to 0. Any questions with that step? I didn't write down all the details. But if you prefer for me to go through it slowly, I can go through it slower. Okay. So now we'll do the Euler-Lagrange equation for y. So you have d by dt of di. Oh, I'm sorry. This should be L bars, right? Of di L bar by di y dot minus di L bar by di y equals 0. All right. So let me see, where do I have any y dots? The y dots is only in the translational kinetic energy. So di L bar by di y dot is my dot. D by dt of that is my double dot. Now I need minus di L bar by di y. Now I have to see, where do I have y. So the first term that I have a y in is the potential energy. I have minus mgy. So di by di y of that is minus mg. And then it's minus the di L bar by di y, so it's plus mg. Now I have the next term where I have the y in it is minus lambda 1 times y. So d by dy of that is minus lambda 1. And then since it's minus the di L bar by di y, it's plus lambda 1. And then finally, I have another term In the last term, I have a minus lambda 2 1 over sine theta y. When I take that derivative, I end up with a plus lambda 2 over sine theta equals 0. Any questions about that? If you want me to go slower and go through all the details to get that equation, I'm happy to do so. Just figure now you've done it a few times, then maybe it's okay to skip a few steps. Our last degree of freedom is phi. So there the Euler-Lagrange equation says that d by dt of di L bar by di phi dot minus di L bar by di phi equals 0. And so where do I have phi dots? I have phi dots in the first term from the rotational kinetic energy. If I take di L bar by di phi dot, I have mr squared phi dot. M and r are both constants. So when I take d by dt of that, I get mr squared phi double dot. Now where else do I have, for the di L bar by di phi, in my equation, phi only shows up in the absolute last term, right? There's a plus lambda 2 r phi. If I take the derivative with respect to phi, I get plus lambda 2 r. And then I have to take minus the di L by di phi. So it's minus lambda 2 capital R. And that's got to equal to 0. So that's our three equations of motion, but we haven't really solved the problem because now we have these undetermined lambdas in them, right? Let me label these equations 1, 2, and 3. So we have, at this point, we have 3 equations with 5 unknowns. The 5 unknowns are x double dot, y double dot, phi double dot, lambda 1, and lambda 2. Remember, we want equations for x double dot, y double dot, and phi double dot. If we can say x double dot equals this in terms of, the other variables, then we're good. That's something we can give to our mathematician friends and they can solve it for us. Alright? So if we just give them these random lambda 1s and lambda 2s, they're going to ask us what's lambda 1 and lambda 2 equal to. So we got to get rid of them. So we need 2 more equations. Oops. So where do we get those 2 equations? Well, we have on the previous page our constraint equations. Okay. Now our constraint equations have F1 has y and x, and F2 has y and phi. But the unknowns that we're interested in are x double dot, y double dot, and phi double dot. So our constraint equations don't have any y double dots, x double dots, and phi double dots. Alright? So we've got to manipulate our constraint equations to have relations between the variables that we care about. Relationships, not relations. That would be weird. Okay. So, well, let's look at F1, right? So, from our F1 constraint, we have let me write it as x equals 1 over tan theta y. tan theta is a constant, right? It's the angle of the plane. So if x equals 1 over tan theta y, I can just take the time derivative of this equation. So I'll get x dot equals 1 over tan theta y dot. That must still be true, right? But you can just take the time derivative of the equation and it's still true. So if I can do it once, I can do it twice. So I'll just put 2 dots instead of 1 dot. Everybody happy with that? So let me box that equation. We call that, call it equation A. Could call it equation 4, but I'll call it equation A instead. And then from F2, we can do something very similar. From F2, we know that I like this. From F2, we know that 1 over sine theta y is equal to r phi. Well, actually, it's more convenient if I put the r on the other side. I'll do the same trick. The capital R sine theta is a constant, right? So I'm just going to take the time derivative twice and call that equation B. So now I have 5 equations and 5 unknowns. It's not so surprising that I can find 2 more equations that relate the x and y and the phi's together, because that's the whole idea, is that they're related. Alright, so now I have 5 equations, 5 unknowns, and the rest is just boring math. Alright, so let's do the boring math. And it's not very difficult now, so it's okay to do. Let me use equation 1 and equation A. So equation 1 was mx double dot equals lambda 1 tan theta. Right? I just moved the lambda 1 tan theta to the other side. And then equation A was that x double dot equals 1 over tan theta y double dot. Let me use that to get rid of x double dot. So then I have m, and instead of x double dot, I'm going to write that as 1 over tan theta y double dot. That's equal to lambda 1 tan theta. And so that ultimately gives me that lambda 1 is equal to m over tan squared theta y double dot. That hasn't solved lambda 1, right? Lambda 1 is still in here in terms of an unknown. It's not in terms of constants. Let me call that equation 1A, because it comes from equation 1 and from equation A. Okay, now let's look at equation 3. Equation 3 from the previous page was mr squared y double dot equals lambda 2 capital R. And then equation B, we're going to use, equation B was psi double dot equals 1 over R sine theta y double dot. So here again, I can get rid of the phi double dot in favor of the y double dot. So I have m r squared, and for the phi double dot, I'm going to write that as 1 over r sine theta y double dot. That's got to equal to lambda 2 times r. As we arrange this a little bit for lambda 2, I get lambda 2 is m over, so if I bring the r over, the r cancels, right? So then I have m over sine theta y double dot. I call that equation 3b because it comes from equation 3 and equation b. Alright? So we've used all the equations except equation 2, so now it's probably a good time to use equation 2. So what was equation 2? Equation 2 was m y double dot plus mg plus lambda 1 plus lambda 2 over sine theta equals to 0. I'm not careful, my g's look like y's, but there are no y's, only y double dots. Alright, so now I know lambda 1 and lambda 2 in terms of y dot, right? So when I plug them in, I'm going to have an equation for y double dot. That was the goal, and that's not going to depend on lambda 1 and lambda 2 anymore. Let's go ahead with that. So we have m y double dot plus mg plus now lambda 1. Lambda 1 is m over tan squared theta y double dot. And then lambda 2 over sine theta is m over sine squared theta y double dot. That's got to equal to 0. That's interesting. It looks like all the m's will cancel, right? So let me divide all the m's out, and let me factor out the y double dot. So the y double dots, once the m's have canceled, I have a y double dot from the first term. Then I have a 1 over tan squared theta term. And then I have a 1 over sine squared theta term. And then plus the term that I forgot, the mg, which I've divided out the m, so it's just plus g equals 0. Okay, so what can we do now? So that's done, right? We have an equation for y double dot, so we could be happy at this point. Since we know how x double dot, right, if I go back here to equation A and B, I have an equation for y double dot in terms of all things that I know. It was very easy for me to find the equation for x double dot using equation A, and similarly, it's very simple for me to find equation for phi double dot using equation B. Right, so the problem is essentially solved. Let's push it a bit further so that it becomes prettier and we have a better understanding of what's going on. So we can work with this term in parentheses. So let me write the equations. I have y double dot. I have 1 plus, now I have 1 over tan squared theta. So tan squared is sine over cos, right? So then 1 over that is cos over sine. And squared is just cos squared theta over sine squared theta. And then it's plus 1 over sine squared theta plus g equals 0. That's convenient that they're let's go. Right. So I have y double dot. So I was saying it's convenient the last two terms are already on the same denominator, right? So then it's 1 plus, I can add the two terms together. I have cos squared theta plus 1, all of that over sine squared theta plus g equals 0. So now I want to add the term 1 to the other ones, so I want to put the term 1 over the same denominator. So then I have sine squared theta over sine squared theta plus cos squared theta plus 1 over sine squared theta. Right, I'm just putting everything over the denominator sine squared theta so I can add them. And y double dot, and now I have sine squared theta plus cos squared theta plus 1 all over sine squared theta plus g equals 0. I have sine squared theta plus cos squared theta now in the numerator, and that's 1, right? So this all becomes y double dot times 2 over sine squared theta plus g equals 0. If I just want to put the y double dots by themselves, I have y double dot equals minus a half g sine squared theta. That's a much prettier form. So it makes sense that we've solved the problem now because we have the differential equation for one of our degrees of freedom, and we know that in reality there's only one degree of freedom that matters. And we know that we can use equation A and B to get the same equations for x double dot and psi double dot. Alright. Now I'm interested in thinking about what were those forces that you can get from the constraints. Remember, those constraint terms, the lambda 1 F1 and the lambda 2 F2, they look like potential energies, and so they must have some sort of force that you can get from them. So I want to see what I get from them. So first I need to know what lambda 1 is. So remember we had lambda 1 up here from equation 1a, right? So lambda 1 is m tan squared times y double dot, and we just found what y double dot was. So lambda 1 is m over tan squared times, there's going to be a minus, and then there's a half, and a g, and a sine squared theta. Well, we call that equation 1a, right? So that's from equation 1a. So now we know what lambda 1 is in terms of constants. So the 1 over tan squared is cos squared over sine squared, right? So that'll cancel the sine squared, and I'll have minus a half mg cos squared theta. That's what lambda 1 is equal to. Lambda 2, that was from equation that I labeled 3b, lambda 2 was equal to m over sine theta y double dot. So that was m over sine theta times minus half g sine squared theta. So we have one sine theta. One of the sine thetas cancels, and I have minus a half mg sine theta. So lambda 1 and lambda 2 are somehow associated with forces. And lambda 1 has something to do with the normal force. So remember, when we did the example last time, we only had one constraint. So we only ended up with one lambda. That one constraint was rolling without slipping. And then the lambda that we found is associated with a torque that makes the hoop spin. Now we have two constraints. So one of the constraints is rolling without slipping. The other constraint is that the hoop must be on the inclined plane, right? So that y over x is tan theta. So now we end up with two lambdas and two kind of forces maybe that have to do with that. So lambda 2 is the same that we got last time, so it has something to do with rolling without slipping, and in fact lambda 2 is related to the torque that makes the hoop turn and roll without slipping. Lambda 1 is related to the normal force that keeps the hoop on the plane. Okay. So let's go ahead now and find the generalized forces that are associated with these. So we have, when we rewrite the equation for finding the generalized forces, we wrote that Qij was lambda I times d by dt of di Fi by di Qj dot minus di Fi by di Qj. Okay, so in our case, the Fi's never depended on any velocities. It's just always going to be zero, that d by dt term. So in our case, this will always just be lambda I times minus lambda I di Fi by di Qj. So this is zero in this case. So how many of these capital Qij's do we need? Well, the I can take two different values, right? We have lambda 1 and lambda 2 for F1 and F2. And then J is for the degree of freedom, so J can be X, Y, or phi. So I can take two values, J can take three values, so there's 6 of these capital Q's. Right? So I've written lambda 1 and lambda 2 there. Let me rewrite F1 and F2 so we have them on this page. So F1, what was F1 equal to? F1 was y minus x tan theta, and F2 was 1 over sine theta y minus r phi. Let's go ahead and evaluate all of these Q's. So the first one is going to be Q1x. So that's going to be minus lambda 1. Alright, so in this case, the Q is going to be minus lambda I di Fi by di Qj. So it's minus lambda 1. So lambda 1 is minus a half mg cos squared theta. So minus that is plus a half mg cos squared theta. And then I need di f1 by di x. So di f1 by di x is minus tan theta. I have a mistake in the notes, because in the notes I don't think it's a positive term, but lambda 1 really is negative. Okay. And the derivative of y minus x tan theta with respect to x is negative. Yeah, I think that should be a minus sign, right? So correct me if I'm wrong, but I think it's should be overall a minus sign, and it's wrong in the notes. So then I have, so tan theta is sine over cos. Oh, it's super wrong in the notes. That should cancel the cos squared. I have minus a half mg cos theta sine theta. Alright, so correct me if that's wrong. I just have to do it in my head here, but I think that's correct. Then we have Q1y. Alright, so I have minus lambda 1, so that's a half mg cos squared theta. And that's got to multiply di f1 by di y. So di f1 by di y is just 1. So all the signs are wrong in the notes. That should be it. So that's the answer for Q1y. Oops. Q1 phi. So that's minus lambda 1, so again a half mg cos squared theta, times di f1 by di phi, but f1 doesn't depend on phi, so di f1 by di phi is 0, and so Q1 phi is 0. Okay, so now let's do the ones that have to do with f2, so then I have Q2x, so Q2x is minus lambda 2, so it's a half mg sine theta, that's with a plus, and then it's times di f2 by di x. So if I look at f2, there are apparently no x's. What am I thinking of in these notes? So Q2x should also be 0. Then we have Q2y. So it's minus lambda 2, so it's a half mg sine theta times di f2 by di y. So f2 is 1 over sine theta y, so di f by di y, di f2 by di y is 1 over sine theta. So that gives me a half mg. And then last, we have Q2 phi, so it's minus lambda 2, so it's a half mg sine theta, And then it's di F2 by di phi. So if I look at F2, it's a minus R phi, so di by di phi of that is minus R. So that's the answer for Q2 phi, minus a half mg sine theta R. So we end up with 6 of these generalized forces. And most of them are rather obscure. And so the only one that I can really get a good physical interpretation of is the last one, which is the torque that makes the hoop turn. And the other ones are related to normal forces and reaction forces. So at this point, maybe we don't care so much about forces anymore. They don't really tell us stuff, right? So we have these constraint equations, and then we do a bunch of mathematics, and then we can end up back to these concepts of forces, or generalized forces, which are often forces or torques or something else that's more abstract. And we're starting to see that we don't really need to care about forces. It's just we have this attachment to Newton's second law, and so we want to think of the forces on the system, but it starts to become quite abstract and unnecessary. Okay, so there are cases where, in fact, you do care about the force. And I think we'll see an example of a case where you do need to find out what the forces are to understand the problem during the tutorial. If you think of, for example, you have a sphere instead of an inclined plane, and you maybe have a block that's sliding down that inverted hemisphere, right? It's a half a sphere. I'm going to erase this later, but imagine you have half a sphere like this, and you have a little block, and you let the block slide down. Eventually, at some angle, it's going to fall off, right? So the condition for the block to fall off the sphere is when the normal force is equal to 0. And that's the only way to really figure out mathematically when the block falls off the sphere, or the hemisphere. And so that's the case where you need to know the forces. And so that's the specific example that we'll do in the tutorial. Any questions about that? Alright, so moving on, if there are no questions. Let's start from the beginning. So if you remember, this description of physics was all obtained from D'Alembert's principle. And that's how we found the Lagrangian and equations of motion. Let's start over with a different principle. And let's call this the Lagrangian from Hamilton's principle. So, Hamilton's principle is now the more fundamental way of doing this whole description of classical mechanics. So I hope to have convinced you that you can build this Lagrangian T minus Z, and then you can get the equations of motion from applying the Euler-Lagrange equation to this Lagrangian. We're going to turn things around now that we know that works, and we're going to change how we formulate classical mechanics. So Hamilton's principle says that there exists a function of the generalized coordinates and their velocities so the generalized coordinates and their velocities in time so there exists this function, I'm going to call it L, and it depends on the Q1 to Qn, Q1 dot, Qn dot, and T. So there exists a function. We don't know what that function is. We saw earlier that T minus V works, but let's suppose we don't know that. So we have a function of the generalized coordinates. All right. So there exists this function. The evolution of the system is given by requiring that the action S is stationary. So the action S we define as it's an integral over time from some fixed time ta to tb of our function L nt dt. Alright, so this tells us the evolution of the system between time A and time B is given by requiring that the action, which is the integral of this function L, be stationary. So that is now the fundamental principle. Earlier when we came from the Lagrangian, we really worked from D'Alembert's principle. And D'Alembert's principle started off from Newton's second law by saying F minus ma equals 0. Now that we know what answer that gives, we reformulate completely classical mechanics and we say there is some function L. We don't know what that function is, but we know that the evolution of the system must be given by the requirement that the integral of that function over time is stationary. So from variational calculus, we know that the Euler-Lagrange equation must be satisfied. So we know, well, we spent some time showing this, that the Euler-Lagrange equation must be true. So d by dt of di L by di tj dot minus di L by di tj equals to 0. Okay? So I'm going to ignore the situation where we have non-conservative forces, because in general, if you consider a system generally enough, then you don't need to include non-conservative forces. Because ultimately the universe as a whole doesn't have any non-conservative forces. The non-conservative forces are typically from our lack of modeling all the details. Right? Friction, for example, is a non-conservative force, but if you really model friction as the electromagnetic interaction of the atoms between the two surfaces, then you'll find that it's actually conservative. And you have to include maybe the kinetic energy of the atoms inside of the materials that are rubbing each other, and the two materials are getting warmer. So if you include all of that, then you don't have the conservative forces. Right? The friction heats up the body. Alright, so we've just imposed this, but we don't know what L is. So Hamilton's principle just says that there exists a function L, such that when you find the stationary values integral with respect to time, you get the equation of the motion. So what could L possibly look like? What could L look like? What are the constraints mathematically or physically that we can place on this function L so that when you do this stuff, it really does describe the system? So it's a little bit difficult to show this in general for when L equals T minus V. So I'm going to run through the argument for a free particle. So let's look at L for a free particle in 3D space. So let's make some general arguments about what L could possibly look like. So a free particle means that there's no forces on the particle, right? So it's a particle that could be moving, but if it's moving, it's at a constant speed. So let's assume that the particle has a speed v. Oh, let's just say let's be more precise and say it's a velocity in some fixed frame of reference. This is a free particle, and it's in empty space, and it has a speed v in some, official fixed reference frame. This is completely empty space, right? So it's completely arbitrary to say that one frame of reference is fixed. You could have another frame of reference that has a constant speed with respect to the first one, and that frame of reference is just as official as the first one. Okay? So consider a second frame of reference moving at constant speed or at constant velocity, capital V, with respect to the first one, with respect to the fixed frame of reference. I put fixed in quotation marks because there's no such thing as officially a fixed frame of reference in complete empty space. It's completely arbitrary, right? So we just have a preferred frame, the spaceship that I'm in, and another alternate frame, the spaceship that you guys are in, moving at a constant speed with respect to mine. So the second frame of reference I'm going to denote with primes, and the first frame of reference I'm just going to call it normal. So if I describe the position of the particle in the fixed frame of reference, that's equal to the position of the particle in the position of the particle, r vector prime, in the moving frame of reference is the same as the position in the fixed frame of reference plus the speed times t of the frame of references, of the relative speed of the frame of references. So I describe the particle's position by r, and you guys are moving at a speed capital V with respect to me, and maybe at t equals 0, our frames of reference coincided. You would describe the particle by r prime to be equal to r plus vt. Right, there's an offset. And so similarly, if you measure the speed of the particle, v prime, you're going to take the time derivative with respect to t, and you're going to get lowercase v plus capital case V. Maybe I'll put a little knob on the top of the capital V's, so that it's clear that they're capital V's. Okay? So that's position in the moving frame and velocity in the moving frame. I suppose I should put moving in quotation as well, since moving and fixed is arbitrary. Okay, so let's make some arguments now. Remember, our goal is to find what L could possibly be. And L will satisfy the Euler-Lagrange equation. We want a description of our free particle that makes sense. And that will give us ultimately a condition on L. So the key notion here is that you are moving in a spaceship, the prime spaceship, moving at a constant speed with respect to my spaceship. And we're both looking at this particle, and we both have our coordinate systems for position and velocity. Now, everybody's moving at constant speed, the particle, you and me. So we should all agree on how to describe the particle. And when we look at the particle, it really shouldn't depend on which spaceship you're on, whether you're on my spaceship or your spaceship. The particle, the description of the particle, shouldn't matter, right? So it shouldn't depend on the frame of reference that you're in. And that makes sense, right? You don't want the laws of physics to depend on which frame of reference you're in. So, okay, actually that's not true, right? We know from special relativity that that's not the case. It does depend on which frame of reference you're in. But we're not doing special relativity here. We're doing classical mechanics. So in classical mechanics, it really doesn't matter which frame of reference you're in, as long as they're inertial frames of reference. We might have time later to see in the course what happens with special relativity. And it's just a modification to this, but it's not a dramatic modification. But hopefully you buy that it doesn't matter what frame of reference you're in to describe the particle. We should agree. It shouldn't depend. Right? L should not depend on the frame of reference. Now, this is a free particle in free space. Right? So there's no forces on it. So this is a homogeneous three-dimensional space. So it shouldn't actually depend on where the particle is in space to what happens to it, right? What happens to it should not depend on where the particle is in space. If, there was a mass there with gravity that was going to disturb our particle, then of course it depends where the particle is in space with respect to some other fixed mass, because the gravity will depend on where you are in space. If this is a free particle, it should absolutely not depend on where in space it is. So the description of the particle, okay, I'll emphasize the free particle, should not depend on where the particle is. So remember, the description of the particle, Hamilton's principle, says that there exists this function L, this magical function L, that will give us a description of the particle. And so for a free particle, that description can't depend on where the particle is in space. So there's a constraint on this function L, that it can't depend on position. So di L by di R, position vector, should be 0. L should not depend on position. And so that means, that's the same if I do it, let's say R is in Cartesian coordinates, so then that's the same as saying di L by di X, or di L by di Y, or di L by di Z. All of those should be equal to 0. So basically, di L by di Qj should just always be 0. It should never depend on the value of the coordinates, because it doesn't depend on space. Okay? Now from Hamilton's principle, okay, let me make another argument. L should not depend on the direction of the particle's velocity. Right, so we have this free particle in space. The equations of motion should not be different if the particle is going in the x direction or if it's going in the y direction. It's completely arbitrary what you call x, y, and z, right? You're in free space. We have this fixed frame of reference, but it is arbitrary. We recognize that. So our description of the particle can't possibly depend on which direction the particle is going. So that means that L can only depend on the magnitude of the velocity. So L must be a function of v squared, not z. So the v squared really means v dot v, right? So this, for example, L could be A times v squared plus v times v to the fourth plus c times v to the sixth, etc., right? That would only depend on the magnitude. So we have two things, right? We have, on the one hand, L is a function of only v squared. What that function is, we don't know. It could be a polynomial. It could be, sine of v squared. It could be something crazy. And two, we know that di L by di Qj equals 0. It should not depend on where in space the particle is. Now we're still working from Hamilton's principle, right? We just don't know what the function L is, but we know that Hamilton's principle should be correct, or we're assuming it's correct. And so we know that from from the Euler-Lagrange equation, that we have d by dt of di L by di Qj dot minus di L by di Qj equals 0. Right, that's from Hamilton's principle. We just don't know what L looks like. Now we just said the second term was 0, right? For a free particle. That wouldn't be true for a non-free particle that's like in a gravitational field, but for a free particle it's true. Okay, so the second term is 0. That means that d by dt of di L by di Qj dot equals to 0. So wait, if d by dt of something is equal to 0, that means that thing doesn't change with time, right? So that means that di L by di Qj dot is a constant. so that means that diL by diQj dot equals the constant. Now remember, L depends on V squared. And V squared has Qj dots in it. There could be mixes of Qi and Qj dots, for example, right? Now, when I take that derivative, or when I say that diL by diQj is a constant, that means that V must be a constant. Or that d by dt of it is going to be equal to 0. So we can already establish that V must be constant. So that, of course, is the equation of motion, is that a particle whipping around in free space with no forces on it is going to have a constant velocity. And so we can already tell that that's true. But it still doesn't tell us what L looks like. But we know that L must depend only on V squared. And now we've all established that diL by diQj dot is a constant. That means that V can't be changing, because otherwise diL by diQj dot would not be a constant. So I'm going to be super specific and say it's constant in time. Alright. But we've done nothing, right? We've used Hamilton's principle, and we've made a few arguments about the symmetry of space and isotropy of space, and we've already basically come up with basically inertia, the law of inertia, one of Galileo's classical mechanics relations, that an undisturbed body is going to continue evolving undisturbed. Okay. Alright, so now we still haven't used the fact that we both should agree on the description of this particle. It shouldn't depend on which frame of reference you're in, right? So, let's get the next page here. So assume we have, a moving reference frame with velocity. So earlier I made the argument that the velocity would be capital V. Now I'm going to make it a very small velocity, and I call it epsilon vector. So then the V primed in that moving frame of reference is just the original V plus epsilon. Okay, so that's just saying that your spaceship has slowed down through a crawl, and it's moving with an infinitesimally different speed than mine, and that velocity, and that velocity is epsilon. Okay. So epsilon will be small. So L, for you guys, is going to be a function of V prime squared, right? It's going to depend on the magnitude of the velocity you measure in your frame of reference that's moving really slowly compared to mine. So that's the same as saying it's L, now V prime squared, I have V prime up there, right? So that's like saying V plus epsilon dotted with V plus epsilon. So that's the same as a function L that would depend on V squared plus 2 times V dot epsilon plus epsilon squared. Okay? And so that, if epsilon is really small, then epsilon squared is even smaller. So I'm just going to ignore it. because that's really small. If epsilon is small, then epsilon squared is really small. Okay, so now, we're talking about the Lagrangian in your frame of reference. What do you think the Lagrangian is compared to what I think the Lagrangian is? And ultimately, it needs to give the same description of the particle because it shouldn't depend which spaceship you're on when you're describing the particle. Okay, so if I do a Taylor series on that, so that's, remember, L at V squared is my Lagrangian, or my function L for the particle. L at V prime squared is your description. All right. So if I look, so L of V prime squared we just saw is the same as L of V squared plus 2V dot epsilon. If I do a Taylor series of that about V squared, right, 2V dot epsilon is small. That's going to be roughly equal to my Lagrangian at L at V squared plus, now doing the Taylor series, I have di-L by di V squared times 2V dot epsilon plus other terms. So that's doing the Taylor series about L of V squared. Right, that's just, so I hope you're comfortable with the Taylor series here, right? So recall the Taylor series. You have f at x plus epsilon. That's roughly equal to f at x plus di-f by di-x times x plus epsilon. Right? So the x in this case is the v squared. So it's di-L by di-V squared, and then the epsilon is the 2V dot epsilon. Okay, so that's the Taylor series. Now, let's put this back into the Euler-Lagrange equation. So remember, we're assuming Hamilton's principle is correct. We just don't know what the function L should look like. Now let me write this one more time. That's your description of the Lagrangian, L of V prime squared. I'm just going to say it's L of V squared plus di-L by di-V squared. And there's 2V dot epsilon, so that's really a constant. I'm just going to call that X. Some constant. It's equal to 2V dot epsilon, right? It's a scalar product between the speed of the particle and the speed of your reference frame. And everything is constant, so that's 2V dot epsilon is just some other constant I don't want to carry around. I'm just going to call it X. Okay? So that's what L of V prime looks like. So L of V prime squared looks like L of V squared plus di-L by di-V squared times some number X. Okay. This number X is not the Cartesian position. Maybe that's not a very good choice of letter. Let me call that maybe C for constant. Okay. Just because I don't want you to look at the notes later and think it's the Cartesian coordinate or something like that. So now, both of us agree on the Hamilton's principle, and so the Euler-Lagrange equation must apply in both cases, right? So the Euler-Lagrange equation is d by dt of di-L of V prime squared by di-Qj dot, and that's minus the term di-L by di-Qj, but we already argued that's always 0, so this is equal to 0. Now if I plug in what I have, So remember, L of V prime squared, I'm going to plug that in. That's L of V squared plus di L by di V times C, di V squared. So I'm going to plug that in. So I have d by dt of di L of V squared by di Qj dot plus d by dt of the second thing. So the second thing is now, so we have di by di Qj dot of that second term, which was di L by di V squared times C equals to 0. Right, I've just plugged in L of V prime squared in terms of L of V squared and that the thing that we have above here. Now if you recall, the first term we already showed that was 0 because that's what's required in my frame of reference. Right, in my frame of reference, I already said that d by dt of di L by di Qj dot is equal to 0, right? So that first term is 0. That means the second term is 0 as well, right? Because it's got to equal 0. So the second term is 0, then the thing in parentheses of the second term is a constant. So we have di by di Qj dot di L by di V squared times C. That's got to equal some constant. Okay. Now the C is a constant, so I can just divide everything by C, and so I have K over C on the right hand side, and I'm just going to call that K again. Alright, so this just tells, I could have taken the C out in front of the d by dt and just divide it out when I had the 0, and so the C disappears, right? So the key here is that di by di Qj dot of di L by di V squared must be equal to constant. Let's go back to the argument here. Earlier I said that di L by di Qj dot is equal to 0. And L can only depend on V. And so when I do di by di Qj dot of L that depends on V, and I get a constant, that means V must be constant in time. So you can kind of make the same argument here. If di L by di V squared now, and then you do di by di Qj dot of that equals a constant, that means L could not have any terms in it that were higher order than V squared. So that means that L equals something times V squared. Right? Because if L had, say, AB squared plus maybe B times V to the fourth, then di L by di V squared would be equal to A plus B V squared, right? And then di by di Qj dot of A plus B V squared would not be a constant. So that BV to the fourth term could not have been there. So you can only have a term in V squared. Any other term would not satisfy the requirement that you get constants. So L must be of the form constant times V squared. All right. So for a free particle, the Lagrangian must be some function where it's a constant times v squared for a free particle. All right. So let's call that constant a half m. So L is a half m v squared for a free particle. And so the point here is that whatever that constant is, it doesn't matter, right? We can use whatever units we want, and so we can maybe choose something that works with what we already are used to working with, and we can call that constant a half m, where m is the mass of the particle. And then L is equal to the kinetic energy. But A did not have to be the mass of the particle. Or in other words, I mean, this is the definition of the mass of the particle. It's the term that goes there with the v squared. So if we use different units of mass, then that constant m wouldn't change the equations of motion. It would just change what we call the units of mass. Okay? So what matters in a system with many particles is the ratios of the constants AI for each particle. So changing the absolute value of AI is like changing our units for mass. So the conclusion here, well, first of all, we found with relatively general arguments about the isotropy of space that the Lagrangian equal to the kinetic energy is an adequate description for a free particle in space. We know mathematically that if we have multiple particles that we can add more terms to the Lagrangian. And what matters is not the absolute value of the terms that we're adding. So it doesn't matter if I call the constant A or if I call it 2A or half m. What will matter ultimately is the ratio of the constants that is attributed to each particle. So the description of the particle will only depend on the ratio of the masses of the particles amongst each other, not on the absolute value of the masses. And just think of that statement as saying we have a bunch of particles. It doesn't matter if I measure their mass in kilograms or grams or or stones. It's only the ratios that matter. So that's ultimately the physical conclusion that we arrived at. We've also seen that mathematically, if I call that constant a half m, it works with what we've been usually calling kinetic energy. Okay. So it's a little bit conceptually difficult to go through this derivation. I'm sure it's a little bit confusing, but please read it again in the notes. And it's a rather important conclusion, I think. Any questions about that? Okay, on Thursday we'll do a tutorial again. On Thursday I will assign assignment 4. Assignment 4 will not be due at the end of next week because that's spring break, so it'll be due following. So you actually have an extra week to do assignment 4 if you were at the work today. Okay, so no questions. We'll talk again on Thursday.